Hey everybody, so welcome back. We're going to do now a more sophisticated method of taking integrals called substitution. Sometimes you'll see it called U substitution. There's a U that's often involved. The actual letter doesn't matter, it's just what a lot of textbooks use for some reason, so we often call it that. But the method is what's really important. This one's going to be different than what we've done so far in the sense that all of the rules we have so far have just been like remembering how derivatives worked. Oh, I have an x squared. If I'd taken the derivative, it must have been an x cubed. You figure out the constant that needs to be there and so forth, right? This is a little bit more of a method. So let's just jump right into it. We're gonna pound through some algebra and sort of a proof-like explanation for what's going on here that I suspect won't hold a lot of meaning for most of us the first time through. Then we'll spend way more of our time actually doing the process, which is the key right now. And then I think as you revisit this proof/algebraic explanation, it'll start to make more sense and become internalized. So let's start there. Let's say we have functions f and g, and let's say that f composed with g of x is differentiable, right? Then, right, according to the chain rule, the derivative of the composition function looks like this, right? Which means if I take the antiderivative I get f of g of x plus c, right? We already know an antiderivative of f prime of g of x. Ooh, I forgot my dx. We already know this antiderivative. I just did it above. I just showed that it's an antiderivative of the integrand. So there's no big secret there. Now, suppose I were to think of the output of g without considering its input, right? Think about composition of functions, right? Our picture is something like, oh, let's say, here's an x, and we do g to it, and we get g of x, and then we do f to whatever that output is, and I get f of g of x, right? That's what composition, one way we can think about it. What if I wasn't really concerned with, right? Maybe this is some kind of process, somebody's computing the amount of gasoline, you know, per hours worked at some oil refinery, and then they're handing that information to somebody who's computing the profits per the amount of gasoline, crude oil at this, I don't know, right? Well, somebody might not care about how many man hours were put in to get it. They just care about the profit part of this, right? They just care about this piece of the graph. So maybe we're going to go ahead and just say, for that person, there's not really a composition of functions. They're just starting with g of x. We'll just give it a name. And they're just putting that into u. They're just putting that number, g of x, they're just calling it u. They didn't see where it comes from. They don't see the x part of it. They just see the g of x at the end. So they put this number u into their function f. So for them, f is just a function of this one variable. And so in a similar way, f prime of u du is just going to be f of u plus c. Right, for the person who only cares about this piece of this diagram, okay? Now notice something though, if u and g of x are really just different ways to write the same thing, then it must be the case that these two things are equal, f of g of x and f of u, right? If if g and u are the same thing, then these two functions are equal. Right? If g of x equals 2 and u equals 2, then f of g of x and f of u are exactly the same thing. So these two things are equal. Well, if the right-hand sides of these two equations are equal, then it must be the case that the left-hand side of this are equivalent. In other words, f prime of g of x, g prime of x dx is equal to f prime of u du under these conditions, right, where u is equal to g of x. Okay, this is the substitution rule. So let me write it out kind of in totality. That's the whole explanation. It probably just felt like a bunch of symbol pushing right now. And then we'll see a couple of examples. Well, we'll see one example right now, and we'll do some more videos a little later. I just want to introduce it here, but it'll start to make sense what this is trying to say to us. Okay, so let me write it out. I would say if u is equal to g of x, if u equal to g of x is differentiable, is differentiable, and its range is an interval I for, this should be, if u is equals g of x is differentiable and its range is an interval I, and f is continuous on I, then, and exactly what we have here, the integral of f prime of g of x, g prime of x dx is equal to the integral of f prime of u du. Okay, now still probably doesn't seem very meaningful yet, and we'll do an example that should help. But the point that what we're going to do is we're going to see things like this. We're going to be trying to integrate something like this that's going to look very complicated, and we're going to instead write it like this, which should hopefully simplify it. Okay, so let's try an example. Suppose I have the following integral: 2x cosine of x squared dx. Okay, so what we're hopefully looking at right now is something like this, so that we can write it this way by using u equals whatever g of x is. So notice what we can be looking for. Look at what we have in our integrand here. There's a g of x and a g prime of x. Right? And so we're often going to look for that. Are there two things in our integrand where one is the derivative of the other? And if you look at x squared and 2x is the derivative of x squared. So I'm going to do something I don't absolutely have to do, just to put it exactly in the form as written there. Right? This is like my f of g of x. This is like my g prime of x. Sorry, excuse me, this is my f prime of g of x. And this is like my g prime of x. Okay? I don't know what f is yet. We'll be able to figure that out pretty easily in just a second. But looking at this and seeing that I have the derivative of another function, that tells me what u should be. U should be equal to the g of x part, and the g of x here is the x squared. Okay? Now, what are we going to do? How do we come up with du? It's not as simple as just writing du. Okay? So here's the idea. We're going to use differentials, right? What we can write, there's a couple ways to think about this. I'm going to mostly think about it algebraically right now and do something that's a little bit inappropriate, but it helps us understand the notation at this point. If I take the derivative of both sides, in other words, if I take the derivative of u with respect to x, right, of this whole thing, I'll get du dx equals 2x. Okay? And then I'm going to move the dx to the other side. as I would a fraction, okay? This is not entirely correct on how we're thinking about it, but as a notation, this is going to work for us. It's going to tell us exactly what to write next, okay? So here's what I'm going to do now. I'm just writing everything again, but using this little key. This over here is like my key, right? Where I see an x squared, I'm going to write a u. So I have cosine of u. Here where I have 2x dx, I'm going to write a du. I have 2x dx, write du. Right? That's exactly what happened here. U replaced g of x, g prime dx was replaced by du. And that's what I've done here. Okay. Now, what's the antiderivative of cosine of u? That's sine of u plus c. But I didn't want the antiderivative with respect to u. I wanted it with respect to x, but I know exactly what to do. U is equal to x squared, so this becomes sine of x squared plus c. And that should be the antiderivative of our original function. Okay, so it feels a little bit like we cheated maybe, like we did a little bit of magic in there. Let's just see if it worked before we try to totally understand this. This one is, a lot of these rules are gonna be a little tricky to wrap our heads around, but they're pretty easy to master, and I believe as you work with them and get more comfortable with some of these ideas, the sense of it will start to emerge. So let's just see that it works. If this is true, then the sine of x squared plus c is an antiderivative to the function in there, which means if we check our work by taking the derivative, sine of x squared, well, this is a chain rule. I get cosine, I take the derivative of the outside, cosine, I leave the inside alone. Oops, I forgot the plus c. Well, I'll just write it here because we know the derivative of the plus c is just 0, so that goes away anyways. And I get exactly what's in the integrand, right? The order of the multiplication here doesn't matter. And so it worked. It gave us the right answer, okay? One way to think about this is that it's undoing the chain rule, right? The derivative direction, we use the chain rule. In reverse, we use substitution. And this little thing we do here is like a little notation to hide the chain rule from us, right? In the chain rule, there's an inside function and an outside function. But we take that inside function and hide it, we collapse it into a single variable. We went from x squared to u. And we also have to find the relationship that has to this derivative when we do the chain rule that's sitting on the outside. That part's a little more complicated, all right? That's the basic idea. There's a whole bunch more examples we're gonna do. I just wanted to introduce it in this one to get us started. So we'll do a whole bunch of examples in the next couple of videos. All right, that's it. Thanks everybody. I will see you next time.